So this is our lecture on solution concentration. It's going to go over molarity, dilutions, and solution stoichiometry. Buckle up, it's 24 slides, so let's start the fun. So first we're going to recap what was in the online lecture from last night's homework. Just a little quick recap of what solutions are. Solutions are homogeneous mixtures. They're aqueous, there can be aqueous solutions that are dissolved in water. Something's been dissolved in water. Homogeneous meaning that you can't see the parts. It's fully kind of enveloped in the other solution. So you're not going to see the little particles of salt in saltwater solution. Remember solvent versus solute. The solute is the thing that's being dissolved. So if we're talking about salt water, it's going to be the NaCl crystals. And the solvent is something that does the dissolving. So it's the water molecules that are dissolving the crystal. So the water is the solvent. All right, and then it also went over the like dissolves like rule, which if you remember, stands for when we have substances that are, like, for example, polar versus non-polar. Polar substances, the ones that have partial charges at the ends, are going to be able to stick to and dissolve in other polar substances. But in terms of polar versus non-polar, a polar substance cannot dissolve in a non-polar substance and vice versa. So over here is a picture of, we've got, the polar substance here being all stuck together and crowded. And basically they're just kind of pushing out the non-polar, on the outside, or vice versa. You could say that the non-polar's on the inside and the polar's on the outside. Either way, you get a separation of the two types of mixtures. All right, so solutions can be made basically two different ways, either by dissolving solids in water or by dissolving gases in water. So let's talk about solids first. So we've seen before that some substances are soluble versus other substances that are insoluble. Soluble substances will be able to dissolve in water and create these homogeneous mixtures or aqueous solutions, right? Insoluble substances won't dissolve in water and therefore just kind of sit there and probably fall to the bottom, all right, and just kind of sit there and they don't actually get dissolved. So in terms of solubility of a solution, there's kind of varying degrees of saturation. Saturation meaning, is there more room for molecules to get dissolved in water? So something that is unsaturated means that, we add just a little bit of solute in there and there's plenty of more room or more availability for that solute to dissolve. So, we've kind of, the water molecules there's more water molecules that can pull apart more solute if we added more. Okay, so that's unsaturated. The next is saturated. So that means that, this solution, we're adding enough salt in order to, if that all of the little water molecules are now, grabbing and attaching to one of the salt ions. So saturated means like that's as much possible, okay, that as much solute possible that you can put in the solution. All right, but there is a way to get a solution that is supersaturated. And supersaturated means that it technically has more solute than should be able to dissolve. In order to get a saturated solution, typically you have to heat up the solvent and it will be able to it'll be able to dissolve more solute than typically if it wasn't at a higher temperature. All right, so we've also seen in the past electrolytes versus non-electrolyte solutions, where electrolyte solutions, if you put that in, if you hook up a, light bulb or little electrode to it, it would conduct electricity. Right, so electrolyte solutions conduct electricity. We're going to do a lab after Thanksgiving to see that. And non-electrolyte solutions, non means don't conduct electricity. So there's going to be a difference in those types of solutions as well. Now, The second way to make a solution is to dissolve gas in water. And so you can think of, good old Coke or any kind of soda can that has the carbon dioxide shoved and dissolved into the water. That we can consider a solution. And so the solubility of gases increases with temperature and pressure. In fact, that's how they create, or that's how they get the carbon dioxide in the water for soda, is that they'll raise the temperature of the water that they are using, and they'll pressurize it in order to get the carbon dioxide to kind of get in and amongst the water. So that's why when you pop the top of the can, you hear the psh, it's like the release of pressure, and we're also going to get some carbon dioxide release as well. All right, so when it comes to solutions, we can talk about solution concentration. So some solutions will be dilute solutions. They contain a small amount of solute relative to the solvent. And other times you'll have a more concentrated solution, meaning that there's more larger amount of solute relative to the solvent. So if you think about it in terms of like Kool-Aid or any of those little powder packs that you can add to water, if you only add a little bit from the powder pack, it's not going to taste very good, and B, it's because there's more water than there is sugar, so it's a dilute solution. Now, if you add like 2 or 3 packs to your water bottle, then you're talking a concentrated solution. You've got a much larger amount of that sugar solute relative to water. So you can even see it, when you do that, you can even kind of tell solution concentration with the color. A lighter color being dilute solutions, and a darker color being concentrated solutions. So although that doesn't obviously happen with most solutions, a lot of solutions that we use in chemistry are colorless, and so you can't really tell. You can't use the color in order to tell how concentrated the solution is. So to figure out how concentrated a solution is, there's a couple of things that we can use. The first one is called mass percent. Okay, so mass percent is a common method of reporting solution concentration. It's basically the mass of the solute over the mass of the whole solution. So here's our our equation here, where you've got the mass of the solute on top, and then if you add the mass of the solute plus the mass of the solvent as like the total mass of the solution, then you've got that on the bottom, and you multiply it by 100 to get a mass percent. So it's almost like saying it's the grams of solute per 100 grams of solution, 100 being the full 100%. So let's work with an example here of mass percent. So it says, suppose you want to calculate the mass percent of sodium chloride in a solution containing 15.3 grams of sodium chloride and 155.0 grams of water. All right, so we got to figure out the mass percent. Again, here is your equation for that. We have the mass of the solute versus both the solute and the solvent. So we've got the mass of the solute here. We're going to plug that in up on top. We have 15.3 grams of sodium chloride. And then we are also given the mass of the solvent. We have 155.0 grams of water. So we have to add those together to get the mass of the whole solution. Because remember, the solution is not just the water, but the water and the salt. So that's a total of 170.3 grams. So if we do 15.3 and divided by 170.3, we're going to get a percentage of 8.98%. And so what that means is that in that solution, we have 8.98% sodium chloride by mass. All right, so here's another example for you guys to try. So you guys can pause the video and take a look at this one, and then unpause it when you guys are ready for the solution, meaning the correct answer. Ha! All right, so this one says calculate the mass percent of a solution containing 27.5 grams of ethanol and 175 milliliters of water. Assume the density of water is 1.0 grams per milliliter. So, of course, this is not going to be as easy as the examples. These you try it ones never are. And so what you'll have to do is we've got the amount of solute here, 27.5 grams of ethanol, and we have the solvent, but instead of giving you just the grams of water, we've given you the volume and we've given you the density. So guess what? You will have to do the density equation in order to find the mass, which then you can plug into your mass percent, right? Percent mass equation. So go ahead and pause it here. Take a few minutes to figure it out, and then you can unpause it and see if you did it right. All right, so hopefully you got 13.6%. When you plug in the volume and the density to the to the density equation, you should have gotten a mass of water of 175 grams. When we plug it into the mass percent equation here, we're going to get the grams of the solute, the ethanol of 27.5 divided by the total mass of the whole solution, so the water plus the ethanol, which is 202.5. And then when you take the percentage of that, you should have gotten 13.6%. So this should be of no surprise by now, but we can use this mass percent of a solution as a conversion factor between the mass of the solute and the mass of the solution. We've seen something earlier with this, with percent of mass composition, when we were talking about, you know, how much sodium in sodium chloride and whatnot. We could use that as a conversion factor, and this the same way. So we could basically say, hey, we've got grams of solute versus 100 grams of the solution. So we can use that as a conversion factor. Here's an example. If a solution contains 3.5% sodium chloride, then we can use these as conversion. We can use that as a conversion factor. Basically, what that means is that you've got 3.5 over 100, right? So 3.5 grams of NaCl over 100 grams of the whole solution. So if you need to convert grams of solution to grams of NaCl, you could use this conversion factor here. Or if you need to do it the other way, you need to convert grams of NaCl to grams of solution, then you would just use the bottom one where the 100 grams is on top and the 3.5 grams is on the bottom. So let's take a look at an example here. It says a sample from Lake Nyos contains 8.5% carbon dioxide by mass. Determine how much carbon dioxide in grams is contained in 28.6 liters of the water solution. So we're going to assume the density of the solution is 1.03 grams per milliliter. All right, so what are we going to do first? Well, we're given liters of our solution. We can convert that to milliliters of the solution. We can plug it into our density equation, or we could just use the density equation as a conversion factor to get to grams of solution. And then from grams of solution, we could use our percent composition in order to get finally grams of carbon dioxide. So let's see how this is going to work. So we're going to start off with our liters of solution. And in order to be able to use our density as a conversion factor, we need to turn liters into milliliters. So we know that 1,000 milliliters is equal to 1 liter, that should say 1 liter of solution. Oh, I see the spacing is a little off. So here's your liters down here. In your printed notes, it should be just fine. So we're going to basically, you're going to get rid of liters of solution by converting it to milliliters. And now once we have the milliliters of solution, we can use the density in order to convert milliliters to grams. So we'll have 1.03 grams on top and 1 milliliter on the bottom. And that's going to cancel out the milliliters and milliliters. So now we're in grams of solution. And so the last little part is, now that we've got grams of solution, we can use our percent composition of carbon dioxide in order to get to grams of carbon dioxide. So we know that it's 8.5%. So that means for every 100 grams of solution, we have 8.5 grams of carbon dioxide. So we're going to use that as a conversion factor. So we have our 8.5 grams of carbon dioxide on the bottom and 100 grams of solution on top. That will cancel the other grams. And so when we do all of the math, we'll end up with 2,500 grams of carbon dioxide in the water. All right, so here's another example that you guys are going to try. A soft drink contains 11.5% sucrose, C12H22O11 by mass. What volume of soft drink solution in milliliters contains 85.2 grams of sucrose? All right, and so we're going to, because we're asked to find the milliliters, we're going to need to use density as a conversion factor as well. So the density, we're going to assume the density of this soft drink is 1.04 grams per milliliter. All right, so think about the steps that you need to take, where you're going to start, what you need to end up with, and go ahead and pause this, try it, and see, and then you can unpause it to see if you did it correctly. All right, so hopefully you started with the 85.2 grams of sucrose. And the first thing we're going to use is the conversion factor with the percent mass. So we've got 11.5% sucrose by mass. And so what that means is we've got 11.5 grams of sucrose and 100 grams of the solution. So we're going to use that as a conversion factor in order to cancel the grams and the grams. So now that we've got grams of solution, we can use the density in order to get to milliliters of solution, because 1.04 grams is equivalent to 1 milliliter. So in the end, you should have gotten 712 milliliters of soft drink. So when you open up your 2-liter bottle and you pour yourself about 712 milliliters of that soda, which is like a little more than half a liter, that's a lot of soda. You've just consumed 85.2 grams of sugar. Yum. All right. Let's take a look at a second way in order to specify solution concentration, and that is called molarity. So we have percent mass, which is the percentage by mass in a solution, and now we've got this thing called molarity. So molarity is the second way to express solution concentration, and it is basically stated as moles of the solute over liters of solution. So here is the equation for molarity: moles of solute divided by liters of solution. So this is what we use most of the time in chemistry and in your labs and all that stuff in order to indicate the concentration of a solution. So the more molarity, the more moles of solute versus liters of solution. The less molarity that you see on the bottles, the less solute that's in there. All right, so this picture down here is just kind of showing you, that we can use molarity in order to make certain concentration solutions in the chem lab. So let's see how this works. Here's an example. It says calculate the molarity of sucrose solution made with 1.5 moles of sucrose diluted to a volume of 5 liters of solution. So molarity is super simple. It's just moles divided by liters. So we have the moles of sucrose and we're given the liters of solution. You just divide the two and end up with your molarity. So in this case, it's a pretty dilute solution, 0.32 molarity. And you can kind of tell that because like 1.5 moles in 5 liters of solution, that's a whole lot of volume. So it's not going to be very concentrated at all. So you guessed it. Here's another you try it practice problem. Calculate the molarity of a solution made by putting 15.5 grams of sodium chloride into a beaker and adding water to make 1.5 liters of sodium chloride solution. So, of course, it's not going to be exactly like the example we just did. In fact, here we're given grams instead of moles. So by now it should be second nature, converting grams to moles. So you're going to do that and then plug it into your equation. So go ahead and pause and take a few minutes to solve the equation or solve the problem, and then we'll take a look and see if you did it correct. All right, did you do it right? You should have ended up with 0.177 molarity solution. So we take our grams of sodium chloride and turn it to moles, right? By using our periodic table as a conversion factor, you get 0.265 moles of NaCl. And then we'll plug it into our molarity equation here, moles divided by liters. So 0.265 divided by 1.5 gives you 0.177 molarity. All right, one more time, guys. Guess what? We can use molarity as a conversion factor between moles and liters of a solution, because remember, molarity is just moles divided by liters. So if we have the number of moles in 1 liter, that can be used as a conversion factor. So here's an example. If a 0.5 molarity NaCl solution contains 0.5 moles of NaCl for every 1 liter of solution, right? We can use that as a conversion factor. If we want to convert liters of solution to moles of NaCl, okay, we will use this one here with the 0.5 moles on top and the liters on the bottom so that they cancel whatever we were just, in. And then, or if we need to convert moles of NaCl to liters of solution, we could use the second one where the liters are on top and the moles are on the bottom to cancel out whatever moles we started with. So see, we can use molarity as a conversion factor in lots of situations because it just means that it's the moles of solute per liter of solution. So let's take a look at an example. It says, determine how many grams of sucrose are contained in 1.7 liters of 0.758 molarity sucrose solution. So if we take a look and we kind of think this through, we are going to need to start with our liters of solution, and we can use the molarity, right? So use molarity in order to convert it to the moles of sucrose. Okay, and then once we have moles, we can get grams by blinking our eyes. I mean, it's that simple, right? Hopefully by now it should be that simple for you. So we'll use our periodic table here in order to convert moles to grams. So that's exactly what we're going to do. If we take a look down here, we start out with our liters of solution, 1.72 liters. We know the molarity. The molarity is 0.758 molarity, so that means there's 0.758 moles of sucrose in 1 liter of solution. Again, in this slide, it's a little off. In your notes, it should be perfect. So that's going to cancel our liters of solution units. And then once we've got the moles of sucrose, we can convert it to grams of sucrose, right, by using our periodic table. If we add up 12 C's, 22 H's, and 11 O's, we're going to get 342.34 grams of sucrose per mole. And so those moles are going to cancel, and we're going to end up with our answer, which is 446 grams of sucrose. All right, you guessed it. It's another you try it. So here we go. How many liters of a 0.11 molarity NaOH solution contains 1.24 moles of NaOH? All right, so if we're given molarity, then basically this number here, if that's the molarity, that's going to be your conversion factor. So take a few minutes, pause, and solve the problem, and then you can see if you did it right. All right, how'd you do? How'd you do? Did you get 10.9 liters? Hopefully you did. Here's how we solve that. So we're going to start off with the moles of NaOH, right? So we identified this as molarity as our conversion factor, so we're not going to start with that. We're going to start with the other guy, moles of NaOH, and then we'll use our molarity as a conversion factor. So remember, molarity is moles per 1 liter. So that means if we have a 0.114 molarity NaOH solution, it means that there's 0.114 moles in 1 liter of the solution. So we can use that as a conversion factor. And then once we do the math, we'll end up with our answer of 10.9 liters. All right, so let's take a look specifically at some certain types of solutions that we can have. So, basically ionic, type of substances versus molecular types of substances. So the concentration of a solution containing a molecular compound, remember that means non-metal compounds, right? So non-metals, H2O, CO2, like any of those that are non-metal combinations. So the concentration of a solution containing a molecular compound usually reflects the concentration of the solute as it actually exists in solution. Meaning that, remember, molecular compounds are not going to break apart into ions because they're not ionic. They are molecular. They hold together a lot better. So, when we say that a 1.0 molarity glucose contains 1 mole of glucose per liter, it is what it is, okay? Now, on the other hand, ionic compounds, right, are made up of metals and nonmetals, okay, which break apart into ions in solution. So this is our metal and nonmetal combos. So those guys, we just talked about at the very beginning of this lecture, that those guys, water's going to break them apart, okay, into their ions. So a concentration of a solution containing ionic compounds actually reflects the concentration before it is dissolved in solution. Okay, so here we've got 1 molarity of calcium chloride actually contains 1 mole of the calcium ion per liter and 2 moles of the chlorine ion per liter, right? Because we got to take a look at the actual formula, right? In this compound, we've got 1 calcium. So if we have 1 mole of calcium chloride, that means we have 1 mole of calcium ions. And we have 2 moles of, or so we have 2 chlorine atoms in this compound. So if we've got 1 mole of calcium chloride, then technically we have 2 moles of the calcium, the chloride ion. So this is the same thing that we've talked about earlier in, I think, unit 1 or 2 when we were talking about mass percent composition within a compound. Okay, so hopefully this does not look new to you, but it's just kind of a reminder. So when we're working with concentration of a solution of an ionic compound, that concentration reflects the concentration before it gets dissolved in the solution. So let's see what this means then. So we've got an example. Determine the molar concentration, meaning the molarity. Molar concentration is the same as molarity. Right? So determine the molarity of sodium ion and phosphate ions in a 1.5 molarity sodium phosphate solution. So remember, 1.5 molarity is the the molarity of the solution before it gets dissolved. So when it gets dissolved, we're going to be breaking apart this ionic substance, right? And here we've got 3 sodium ions, right? Versus 1 PO4 group. Right, remember that's a polyatomic ion. So we got 1 PO4 group and we've got 3 sodium ions. So when we're trying to figure out the solution of the parts, we have to keep that in mind. So the molarity of sodium is not just going to be the 1.5, but there's 3 sodium ions in there. So we have to multiply the molarity by 3. So the molarity of the sodium ions are actually 4.5 molarity, because we've got 3 of those ions that are going to be dispersed in the solution once it's all stirred together and broken apart. Now, the phosphate ion, okay, there's only, 1 of those in that compound. And so because there's only 1, we're going to do 1 times the molarity, 1.5. So in here, we've got the molarity of the phosphate ion being the 1.5 molarity. So here's an example for you guys to try. Go ahead and read through it and pause and then see if you came up with the correct answer. All right, take a look and see if you got it right. Hopefully you guys identified the molarity of the calcium ion as being 0.75. Okay, in this solution, we have one calcium ion in the compound. All right, and so 1 times 0.75 molarity is 0.75 molarity. On the other hand, we've got 2 chlorine ions in this compound, and so we have to multiply the molarity by 2 in order to get all of the molarity for the calcium ions. So chlorine ions. So 2 times 0.75 is 1.5 molarity of chloride ions. All right, so hopefully those two ways of saying the concentration of solutions make sense to you, the percent mass and the molarity. Now what we're going to do is talk about solutions that are already in the solution like liquid state, but we need to maybe dilute them. Okay, so this happens a lot well, I do this all the time when I'm making acids. A lot of the acids come in a more concentrated liquid form, and so I have to dilute them to whatever concentration that we need in a particular lab. So I do this constantly. This is what we call solution dilution. So stock solutions are solutions of a stored concentrations, higher concentrations typically. And so in order to, use the solution in a particular concentration that we need, we're going to need to dilute it. And so this works by this equation here. So we've got a lot of equations in this lecture, so hopefully you guys can keep them straight. When to use molarity, when to use mass percent, when to use dilution. So here is M1 V1 equals M2 times V2. And so the ones I usually, say, hey, that's the stock solution information. And then the 2 side is the dilution side of the information. All right, so let's take a look at an example as we walk through how to use this equation. So it says a lab procedure calls for 5 liters of a 1.5 molarity KCl solution. How do you prepare this solution from a 12 molarity stock solution? Okay, so basically what we need to know is how much stock solution do we need in order to make 5 liters of this 1.5 molarity solution, right? So our M1s, remember, is the stock side. And our 2s is the new, diluted side. Right, so we're going to plug in the information that we need on the correct sides. So for the stock solution, we are given the molarity, but we don't know how much to use. That's what we need to figure out, right? So V1 is going to stay as a variable. And then on the other side, we have we are given our volume of the new solution, and we're given the molarity of the new solution. So we'll plug both of those into those variables right there. All right, so when we solve for V1, we do a little algebra, solve for V1, we're going to end up with an answer of 0.625 liters, okay? So what that means is that you need to pour out, from your stock solution, you need to pour out 0.625 liters, right? That's the same as 625 milliliters. So you pour out 625 milliliters of your stock solution, and then you need to add water to get up to your full volume of 5 liters, right? So we would, pull out the 625 milliliters and then add like whatever the 4,375 milliliters of water in order to make the full 5 liter mark. So getting your answer is kind of only partially the full answer, because you need to make sure that you understand that that's how much stock you need, and then you need to fill the rest up with water to get to your final volume that is required. So here's an example for you guys to try. Go ahead and read through this, pause, and then you can unpause to see if you got it correct. All right, so This question, how it's asked, can be kind of a little tricky to figure out which is the stock versus which is the new solution. So you do want to make sure that you take careful notice of the verbal like syntax cues as to which is the before the stock solution versus which is the after, which is the new solution. So, the key words kind of here is to obtain. So that means, you're going to get the solution, the 1.0 molarity solution in the end. So that would mean that part is the new or the dilute. That's your to side, right? So that means that this here is what you start with. So that's your, one side, your M1 and your V1. So you do need to make sure, like, if you read it through the first time, you're like confused as to which numbers belong where. Typically, they're, given as kind of a set. So, 0.1 liters of a 15 molarity solution, that kind of goes together. So you're going to put those on one side. And to figure out what side you put it on, take a look at those keywords like to obtain or to get or, that kind of thing. So hopefully you got in the end 1.5 liters. All right, so the final kind of topic in this lecture is solution stoichiometry, because a lot of chemical reactions take place in the aqueous solutions. So we've seen it before. A lot of double replacement reactions are going to be two liquids that you're mixing together to make something new, right? So precipitation reactions, neutralization reactions between acids and bases, and then even some where you're mixing two solutions and you get gas bubbles happens. And so those guys are in, aqueous solutions. So we can use the molarity as a conversion factor between volume and moles for aqueous substances and reactions. So basically what this means is that if you start out with a certain volume, you can use molarity in order to get to moles of that solution. And then, you could use your mole ratio here from the equation, or from the reaction equation. You use your mole ratio to go from moles of A to B. And then again, you can use the molarity to go from moles to volume of solution B. So let's see how this works in real life. So this example gives us a reaction between sulfuric acid and sodium hydroxide in order to make sodium sulfate and water. Okay, so this is a neutralization reaction between an acid and a base. We've got a balanced chemical equation here. All right, and so we're going to use that in order to help answer the question. How much 0.125 molarity NaOH solution do we need to completely neutralize 0.225 liters of a 0.175 molarity sulfuric acid solution? So the words how much indicate volume, right? So we're going to need to figure out the volume, like the liters, of this NaOH solution in the end. So we have to start with where we're given. So we're going to start with what we're given is the liters and the molarity. Molarity, remember, can always be used as a conversion factor. So we're never going to start with molarity. We'll start with the other piece of information, the liters. So we have 0.225 liters of sulfuric acid, and we can use the molarity, right, as a conversion factor to convert to moles of our sulfuric acid. And then we can use our mole ratio from the equation, right, up here, in order to go from moles of H2SO4 to moles of, NaOH. Okay, so that's a 1:2 ratio. And then we can again use molarity. Since we're given the molarity of the NaOH solution in the end, we could use molarity to figure out the number of liters. And so this down here, this is what it looks like down here when we're kind of writing out all of the conversions. So we'll start out with the 0.225 liters. Cancel the liters as we use molarity, which is the 0.175 moles per 1 liter. Then we have to take a look at the ratio. It's a 2-to-1 ratio, like we said, so 2 moles of NaOH to 1 mole of H2SO4. And then finally, we'll use the molarity of the NaOH solution in order to convert from moles to liters. Since 0.125 molarity means the same thing as 0.125 moles in 1 liter, we can use that as a conversion factor to get the liters in the end. And when you do the math, you get 0.630 liters of the NaOH solution. All right, so you guessed it. Here's one for you to try. It says, consider the precipitation reaction. Potassium iodide and lead nitrate to react to form lead iodide and potassium nitrate. So here's your question. How much 0.115 molarity Ki solution in liters will completely precipitate the lead ion in 0.104 liters of 0.225 molarity lead nitrate solution? Okay. All right, so go ahead and pause it, spend a few time with it. You may need to work with a partner with this. This is, I don't know, maybe tricky in a sense of how it's worded. Okay, but see if you can figure out. We're going to need to figure out how much in liters. You need to end up with liters of Ki in the end. So go ahead and pause it and see if you can figure it out. All right, hopefully you guys ended up with 0.407 liters of Ki. So again, like we did with the previous one, we'll start out with our liters of lead nitrate solution, use the molarity to find the moles of the lead nitrate. You could even, kind of rationalize with the ions that, because we've got 1 mole of PbNO32, for 1 mole of that, there's 1 mole of the Pb ions. This part is kind of, optional. But we will use the mole ratio, right, from the equation here to plug in to switch from moles of lead to moles of Ki. And then finally, we'll use the molarity that we're given to go back down to liters. So when we do all that, we should end up with 0.407 liters of potassium iodide solution. All right, so here is one more for you guys to try. So how many milliliters of a 0.112 molarity sodium carbonate solution will completely react with 27.2 milliliters of a 1.35 molarity nitric acid solution according to the reaction? So again, take a few minutes to read through it, to work it out, and then unpause it when you're done to see if you did it correct. All right, so hopefully you ended up with 16.4 milliliters. And that concludes our 24-slide adventure of stoichiometry, dilutions, molarity, all the solution stoichiometry stuff. So if you have any questions, make sure you come see me next class and or in future classes before we have a quiz or a test on this. In the meantime, you're going to practice some of these on a Socrative and get some more practice. All right, we'll see you later.